Hello, students. Let's do another recursion. Okay, so we're going to talk about a very famous math problem called the collatz conjecture. So how does the collatz conjecture work? Well, uh, what we're going to do is we're going to have a certain process. And this process is given a number. What we're going to do is if it's even, we divide by 2, given an integer. Even integer, divide by 2. By the way, we're sticking to the positives. Even integer, divide by 2. Got it? If it's odd, what I'm going to do is I'm going to make it even by multiplying by 3 and adding 1. Okay, so if it's even, I divide by 2. If it's odd, I multiply by 3 and add 1. Uh, okay, well, let's try to write this in Python. So I'm going to return n divided by 2 if n mod 2 is equal to 0, else 3 times n plus 1. So we can see what happens if I take the collatz of 5, right? C of 5 or collatz of 5. I mean, there's lots of collatz Catalan. There's lots of big C functions. So let's call this collatz. So collatz of 5 is 16. Collatz of 16 is 8. Collatz of 8 is 4. Collatz of 4 is 2. And collatz of 2 is 1. Let's try some more examples. Collatz of 3 is 10. Collatz of 10 is 5. And then collatz of 5, well, we know that's going to be 16, 8, 4, 2, 1. So the thing is we're getting down to 1 by repeatedly using collatz over and over again. Okay, that's nice. And we're in the section on recursion, and you didn't use recursion in order to make this collatz. So what are we doing here? I mean, okay, there's a famous problem in mathematics, unsolved at the time of the recording of this video. I'm quite sure it's going to be unsolved for, I mean, likely my lifetime. But the conjecture says that no matter what number you start with, you eventually get to 1. And you might say, well, why can't we just check this with computers? Well, you can check for some big numbers with computers, right? But you're never going to check all the numbers with computers, right? Because computers would have to run forever. So what we're going to do is we're going to try to figure out if we can get to 1 from each of these numbers, from any given number. And what we're really interested in is, let's see, how long? Let's try to measure how long it takes to get to 1. That's a nice exercise. So how many steps does it take to get to 1? Let's see. So let's make a function called collatz steps. So for instance, 1 should just return 0 because it didn't need any steps. It started at 1. So I want to return 0 if n is equal to 1 already. But what if it's not equal to 1? Well, then what I wanted to do is I wanted to run collatz function and then run the collatz function and run the collatz function. And I want to add 1 every single time I run the collatz function. And we can do this with recursion. And here's how. You see, if I take a number and I want to know how long it takes to reach 1, what I could do is I could run the collatz function once and then see how long it takes that new number to reach 1. So now I've run it once, and then I see how long it takes the new number to reach 1. It's going to be that many steps plus that first step in the beginning. Say that one more time. If I want to know how long it takes a number, say 5, whatever, in order to reach 1, what I do is I run the function on 5 once. I get to 16. And then I see how long it takes 16 to get to 1. And then I realize I ran it once in the beginning, so I have to add 1 to that total count of the number of times I ran the function. So this actually is something that we can do very nicely in a recursive way. So otherwise, it's going to be 1 plus the collatz steps of what happens if I run collatz once. Yeah, so just collatz then. So basically, If n is already 1, it took 0 iterations in order to reach 1, because I started at 1. Otherwise, what I'm going to do is I'm going to run collatz once. I'm going to find out how many steps it takes that number, and I'm going to add 1 because I ran collatz once. Let's see if this works. So this should be 1, which works. This should be 2, which works. Let's try collatz of 5. 5 steps. Did I get 5 steps? Let's see. 1 step to get to 16, 2 to get to 8, 3 to get to 4, 4 steps to get to 2, and 5 steps to get to 1. So this is really nice to do recursively. It's super short. We're really doing a ton of math here. And we can run all sorts of experiments, like let's take the collatz steps of the first 20. Oh, of the first 20. That was silly. I shouldn't have given it 2 arguments. I was thinking about my range. I want this to go from 1 to 21. So these are the number of steps it takes for the first 20 positive integers in order to reach 1. You'll see it takes 1 0 steps, it takes 2 1 step, and it takes 3 7 steps. And you can sort of see how fast these are growing. We're really doing what we would call experimental math here. We're getting conjectures, we're getting data. Can we find some lower and upper bounds on how many steps it'll take given an n in a certain, given a certain value of n? All of that would be very valuable. But obviously that isn't known, because if we can get an upper bound on how many steps it takes, well, then we could use that to show that it always does return to 1. But that's a nice example of doing something quite sophisticated in Python without a lot of lines of code.